If you've ever wondered how self-driving cars actually navigate busy streets, or how drones map out disaster zones in real time, the answer is LIDAR. But here's the thing, the LIDAR systems we rely on today have a massive, fundamental physics problem holding them back. Well, in this explainer, we're looking at how researchers at MIT have literally just cracked the code. They've solved a major optical puzzle that has stumped engineers for years, and it's all about the geometry of light. Okay, let's dive right into this. We're going to start by looking at the current LIDAR bottleneck. Then we'll explore the solid-state dilemma that engineers ran into. From there, we'll unpack MIT's clever antenna innovation, look at the intense engineering balancing act required to pull it off, and finally wrap up with what this all means for the future of navigation. Part 1. The LIDAR bottleneck. To really grasp why MIT's work is such a game changer, we first need to understand the hardware bottleneck we're currently stuck with. Traditional LIDAR systems, those bulky things you see spinning around on top of autonomous test vehicles, they work by physically shooting out rapid pulses of infrared light to build 3D maps. But they're bulky, they're incredibly expensive, and because they rely on mechanical moving parts, they eventually just wear out. So the absolute holy grail here is silicon-photonics LIDAR. This tech uses semiconductor technology to steer light electronically with zero moving parts. It's essentially an optical phased array on a tiny, cheap, compact chip. Sounds perfect, right? Part 2. The solid-state dilemma. So while silicon-photonics sounds like the ultimate solution, engineers immediately slammed into a massive roadblock when actually trying to build these chips. It turned into a classic Goldilocks problem about exactly how far apart to place the microscopic antennas on the chip. The first hurdle they hit is called crosstalk. See, on a silicon-photonics chip, you've got a series of integrated antennas emitting light. But if you pack them tightly together to get a nice wide field of view, the light waves just interfere with each other. It's kind of like trying to have a very private, complex conversation in a crowded, noisy room where everyone is standing shoulder to shoulder. All the voices just bleed together into pure noise. And the harsh reality of that setup? Massive distortion. In a conventional optical phased array, if you pack the antennas tight enough to get that wide field of view, the coupling, or the interference between them, reaches roughly 100%. The sensor's accuracy is completely ruined. The beam of light just becomes an absolute mess. So you might be thinking, the obvious fix is to just move the antennas further apart, right? Just give them some breathing room. Well, if you do that, you trigger the other side of the dilemma, which is grating lobes. When antennas are spaced too widely apart, the array suddenly generates duplicate copies of the light beam, and they go shooting off at completely different angles. And this builds into a real-world disaster pretty quickly. If you spread the antennas out, these grating lobes create duplicate beams, which means the primary beam you actually want to use becomes indistinguishable from its clones. This severely limits the sensor's field of view. An autonomous car, for example, suddenly only knows what's directly in front of it for a very, very narrow range. It wastes critical energy, and honestly, worst of all, it creates false positives. The sensor might literally see a pedestrian that isn't even there, or entirely miss a car that actually is. So simply changing the distance between the antennas, absolute dead end. Part 3. MIT's clever antenna innovation. Since changing the distance wasn't working at all, a team at MIT realized they needed a total paradigm shift. Instead of focusing on where the antennas were placed, they decided to look at what the antennas actually looked like. See, in conventional arrays, every single antenna uses the exact same geometry and the same pattern of tiny ridges or corrugations on its surface. But the MIT team, led by senior author Jelen and Ataros, just threw that rulebook out the window. They designed 3 completely different antenna geometries, with varying widths and different corrugation arrangements. By doing this, they gave each antenna a unique propagation coefficient. Think of it like giving each individual beam of light a completely different set of speed bumps to travel over. And the result of changing that geometry is absolutely incredible. It's perfectly captured in this quote from co-author Andres Garcia Coleto, who said, "Because the antennas have very different propagation coefficients, when we put them close together, essentially each antenna doesn't see the antenna next to it." I mean, it is such a brilliant, elegant concept. By varying the physical shapes, the antennas basically become optically invisible to one another. They don't couple. The whole crosstalk issue is completely bypassed, even when they're packed super tightly together. But wait, this introduces a massive new problem, doesn't it? How on earth do you make completely different, uniquely shaped antennas act as one unified, highly precise sensor? If they all inherently behave differently, how do you steer a single, clean beam of light? Part 4. The engineering balancing act. Well, this is exactly where the sheer physics and mathematical heavy lifting came in for the MIT team. To make these uniquely shaped antennas fire in perfect unison, they had to satisfy three incredibly strict requirements. First, despite being totally different shapes, each antenna had to emit the exact same amount of light. Second, they all had to direct the beam at the identical angle for a specific wavelength. And third, as the beam is electronically steered to scan an area, the emission angle has to shift consistently across the entire array. If even one of these parameters is slightly off, the entire LIDAR beam just falls apart. Lead author Henry Crawford Eng summed up this massive hurdle perfectly. He said, quote, "We require the antennas to have different geometries to reduce the crosstalk, but we need to simultaneously design the antennas to have the same emission characteristics. While it is possible to engineer this, it is extremely difficult." And he's not kidding. They literally had to develop entirely new electromagnetic theory just to describe how these radio modes interact, all before they could even simulate and build the physical antennas. Part 5, the future of navigation. But they actually did it. After working out the theory, running all the simulations, and physically building the silicon-photonics prototype, the real-world results were staggering. 1%. Remember earlier when we said that tightly packing conventional antennas resulted in roughly 100% coupling and just total distortion? Well, in the MIT team's experimental testing, their new design dropped that coupling all the way down to just 1%. No grating lobes, a single precise beam, and they kept a wide field of view. I mean, it's a resounding success. And by solving this fundamental physics problem, the real-world impact is going to be massive. We're talking about significantly safer autonomous driving at high speeds, purely because vehicles will have wide-angle, instantaneous, low-noise vision without dangerous blind spots. It means highly accurate aerial mapping for drones, precision monitoring for construction sites, and because it relies on silicon photonics, it enables cheaper, massively scalable manufacturing. We can stamp these chips out just like computer processors. Senior author Jelena Natros puts it perfectly here. The functionality we demonstrated in this work solves a fundamental problem for integrated optical, phased array technology, enabling future LIDAR sensors that can achieve significantly higher performance. This isn't just some small incremental update, guys. It is a foundational leap forward for solid-state beam steering. So, I want to leave you with this thought to consider. With solid-state LIDAR, now capable of wide-angle, incredibly low-noise vision, entirely contained on a tiny, affordable chip, what machines will we finally trust to navigate our world autonomously? The geometry of light has been solved, and the future of robotics is going to look a whole lot clearer.